Now, in this lecture, we find out the radius of a circle using two different methods. In the drawing, we have triangle ABC. This triangle ABC blocks the circle, or this circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in size. This is angle ACB, that is equal to 75 degrees. And side BC of triangle ABC equals to 2 units in its length. Our mission is to find out the radius of this circle. We start with the first method, and here from point C we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. By doing this construction, we added here the right triangle BDC. I will copy the right triangle BDC in a new page and we will analyze it. So actually, this is triangle BDC that I copied from the original drawing of the question. Here, this is angle BDC that is equals to 60 degrees in size, and side BC equals to 2 units in its length according to what is given in the question. So in this right triangle BDC, cosine 60 degrees equals to dB over BC. Okay, cosine 60 degrees equals to dB over BC. So cosine 60 degrees equals to dB over BC, and BC is 2, so it is dB over 2. Cosine 60 degrees is 1/2. So substitute cosine 60 degrees by 1/2, so 1/2 equals to dB over 2. Here we multiply this equation by 2, and finally we get that dB equals to 1 unit in its length. dB equals to 1 unit. So this nice segment dB equals to 1 unit in its length. We will continue to focus on this right triangle BDC. In the right triangle BDC, sinus 60 degrees equals to DC over BC. Minus 60 degrees equals to DC over BC. So sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC. And BC is 2, so we substitute BC by 2. In conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we will multiply the equation by 2, and finally we get that DC side DC equals to the square root of 3 units in its length. So this is side DC is equals to the square root of 3 units in its length. So in the right triangle DBC, we know that the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside a triangle DBC? We have this angle that is equal to 60 degrees plus this angle that is equal to 90 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Plus the missing angle, in total, it must be equal to 180 degrees. So the missing angle must be equal to 30 degrees in its size. In order to complete the sum of the angles in this triangle DBC to 180 degrees, the missing angle here must be equal to 30 degrees. So angle DCB equals to 30 degrees in its size. It is given us in the question that the big angle ACB equals to 75 degrees. And just like the found out that angle DCB equals to 30 degrees. So the big angle that is 75 degrees, again, the big angle that is 75 degrees minus the small angle that is 30 degrees must be equal to the missing angle that is actually angle ACD. So actually angle ACD, the missing angle ACD must be equal to 75 degrees minus 30 degrees, that is actually 45 degrees. So angle ACD equals to 45 degrees in its size. Actually, this is the missing angle ACD is equals to 45 degrees in its size. Okay. In the next step, I will copy the right triangle ADC in the new page and we'll analyze this right triangle ADC. So actually, this is the right triangle ADC that I copied from the original drawing. We just right now found out that DC equals to square root of 3 units in its length, and this is the missing angle that equals to 45 degrees. We know that the sum of the angles in triangle ADC must be equal to 180 degrees. That is to say 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the missing angle, in total they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. Again, in order to complete the sum of the angles in this triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees in its size. So, those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. In front of those two equal angles, we have those two sides that are equal to each other. That must be equal to each other. That is to say, side AD must be equal to side DC because they are located in front of equal angles. Side AD must be equal to side DC in this triangle, triangle ADC. But we know that DC equals to square root of 3 units. So we can write here that DC equals to the square root of 3 units. And for this equation, AD equals to DC equals to the square root of 3 units. We will derive that side AD is also equals to the square root of 3 units in its length. Here AD equals to the square root of 3 units in its length. You can write down in the original drawing that line segment AD, this line segment AD equals to the square root of 3 units in its length. We will continue to focus on this right triangle, triangle ADC. Here we will implement the Pythagoras theorem. By PT is abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle, triangle ADC, AC squared, that is the square of the hypotenuse, must be equal to AD squared plus DC squared. The square of the hypotenuse equals to the sums of the squares of the perpendiculars. So AC squared, that is the square of the hypotenuse, in the right triangle ADC, must be equal to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. Here we take a root out of this equation, and finally we get that AC equals to the square root of 3 units in its length. So we can write here that side AC of this triangle, triangle ABC equals to the square root of 6 units in its length. Okay, so in the next step I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, rule number 15 is true in any triangle. The radius of a circle that is inscribed by triangle ABC, that could be any triangle, is equals to, so the radius R equals to the area of triangle ABC that blocks the circle over the same perimeter S of the same triangle, triangle ABC. The same perimeter of any triangle is the perimeter over 2. So in the drawing of rule number 15, we have triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC, like in our original drawing. So the radius of this circle, the radius R, equals to the area of triangle ABC that blocks the circle over the same perimeter of the same triangle, triangle ABC. We can actually implement rule number 15 in our drawing, because in our drawing we have also a triangle ABC that blocks the circle, or this circle is inscribed by triangle ABC. For that reason, whenever we have a triangle, whenever we have a circle that is inscribed by a triangle, you can implement rule number 15. So according to rule number 15, in our drawing, the radius, we define the radius of this circle as R. So the radius R, according to rule number 15, will be equal to the area of triangle ABC that blocks this circle over the same perimeter of the same triangle, triangle ABC. Repeat again. this equation is actually the implementation of rule number 15 in our drawing. According to rule number 15, the radius r of this circle that is described by this triangle ABC will be equal to the area of triangle ABC over the same perimeter of this triangle ABC, the same triangle. And the same perimeter of any triangle is the perimeter over 2. The perimeter is the sum of its side lengths, that is to say it is AB plus AC plus BC, and if we divide the perimeter by 2, we get the semi-perimeter S. So, again, the radius of our circle that is described by triangle ABC equals to the area of triangle ABC over the semi-perimeter S. So the area of triangle ABC, the area of any triangle equals to the base of the triangle times the height to the base over 2. All divided by S. So the area of our triangle ABC is the base. We will take the base of this triangle as AB. So the base is AB times the height. The height must create 90 degrees with the base AB. Here, line segment CD creates 90 degrees with the base AB. Therefore, CD is the height to the base. So the height is CD divided by 2. Repeat again. The area of our triangle ABC equals to the base AB times the height to the base, that is CD, over 2. All divided by the semi-perimeter of this triangle ABC. Again, the semi-perimeter is the perimeter over 2. The perimeter is AB plus AC plus BC. AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter S. And again, the semi-perimeter is the perimeter that is AB plus AC plus BC. And after we divide the perimeter by 2, we get the semi-perimeter S. So the area of triangle ABC equals to AB. AB is equal to 3 plus 1. So we substitute AB by square root of 3 plus 1 times the height CD. We already found out that CD equals to the square root of 3 units in its length. So we substitute CD by square root of 3 divided by 2. This expression is the area of our triangle ABC, divided by the semi-perimeter S. And the semi-perimeter S equals to AB, that is square root of 3 plus 1, plus AC. AC equals to the square root of 6 units, plus BC. BC equals to 2 units in its length, here according to what is given us the question. BC equals to 2. So it is BC, that is plus 2, all divided by 2. So this expression is the area of triangle ABC. The value of this expression, that is to say the area of triangle ABC, is 2.366 square units, all divided by this expression, that is actually the semi-perimeter of the same triangle ABC. So the value of this expression in total, it is equals to 3.591 units, and 2.366 or 3.591 is equals to 0.6589. So in conclusion, we found out that the radius R of this circle that is described by triangle ABC is equals to 0.6589 units. And that is the answer to our question. So we finished with the first method. In the next step, I will present to you how to find out the radius of this circle that is described by triangle ABC according to the second method. In the second method, here we will define the center of this circle as O. We will define the point of tendency of tangent BC with this circle as D. We will define the point of tendency of tangent AC with this circle as F. And finally, we will define the point of tendency of tangent AB with this circle as E. We will join points O and D together by a straight line. So point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle, the radius that we are looking for. We will define the radius of this circle as R, so OD equals to R, this is the radius of the circle. And here we actually have rule number 1. According to rule number 1, a tangent to the circle is perpendicular to the radius corresponds to its point of tendency. So, in the drawing we have tangent AB. This is tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. Okay, we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the radius OD of this circle that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. We join points O and D together by a straight line. OE is the radius of this circle that is equal to R. Again, we have the radius OE that is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius O, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and F together by a straight line. OF, nice with OF is the radius of this circle that is equal to R. Again, we have the radius OF that is drawn to point F, that is the point of tendency of tangent AC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius of O, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Okay. In the next step, we focus on the common start point C. Here we can actually implement rule number 2. According to rule number 2, the lengths of two tangents from a common start point to a circle are equal. We have a circle and the common start point P. From the common start point P, we have two tangents to this circle, tangent BA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. In our drawing, if we focus on the common start point C, from the common start point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. So you can write down here that CF equals to CD. CF equals to CD according to rule number 2. Likewise, we focus on the common start point B. From the common start point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. So BE equals to BD according to the same rule number 2. BE equals to BD. In the next step, we join points O and C together by a straight line. And we also join points O and B together by a straight line. And we will prove that the yellow right triangle OBD is congruent to the green right triangle EBO. So, write it down. The yellow right triangle is triangle ODB. We prove that it's congruent to the green right triangle OEB. So why those two right triangles can go into each other? First of all, side EO of the green triangle is equal to side OD of the yellow triangle. They are both the radii of the circle, therefore they are equal to each other. So we can write down that EO equals to OD. Repeat again. Side EO of the green a triangle equals to side OD of the yellow triangle. They are both equal to R because they are both the radii of the circle. In addition, BE equals to BD according to rule number 2. Repeat again. Side BE equals to side BD according to rule number 2. Repeat again. Side BE of the green triangle equals to side BD of the yellow triangle according to rule number 2. And finally, we have OB, that is a common side. Side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself is a common side that belongs to both triangles. Repeat again. Side OB is a common side that belongs to both triangles. So we can write down that OB equals to itself. So we actually proved that all the three sides of the green right triangle BOE are correspondingly equal to all the three sides of the yellow triangle BOD. Therefore, those two right triangles can go into each other according to side rule. So I write it down. So the yellow triangle BOB congruent. This is the sign of congruent. So the green triangle OEB. According to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other. So this is angle OBE in the green triangle. And it is equal to this angle, that is actually angle OBD in the yellow triangle. Once again, angle OBE in the green triangle equals to angle OBD in the yellow triangle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, must be also equal to each other. So if we define one of those two angles as theta, here, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta in total equals to 60 degrees according to what is given us in the question. So 2 theta equals to 60 degrees. Here we divide this equation by 2 and finally we get that theta equals to 30 degrees in its size. So this is actually angle theta that is equals to 30 degrees in its size. In the next step, I will copy the right yellow triangle OBD in a new page and we'll analyze it. So actually, this is the yellow right triangle, triangle ODB that I copied from the original drawing. This is angle theta, angle OBD is angle theta that is equals to 30 degrees in size. And here side OD is the radius of this circle that is equals to R. OD equals to R. So in the right triangle BOD, it is very easy to see the tangent 30 degrees. Tangent 30 degrees equals to OD over BD. OD over BD. So tangent 30 degrees equals to OD. OD is R divided by BD. Here we will multiply this equation by BD and we will get that BD times tangent 30 degrees equals to R. Here we will divide this equation by tangent 30 degrees and finally we will get that BD equals to R over tangent 30 degrees. Okay. So here this line segment BD equals to R over tangent 30 degrees in its length. So I write it down here in the drawing. Side BD equals to R over tangent 30 degrees. Likewise, we will prove that those two right triangles also can go into each other according to side rule. So actually, we prove that the orange triangle ODC is congruent to the pink triangle OFC. So I write it down. We prove that the orange triangle ODC is congruent to the pink triangle OFC. So why those two triangles can go into each other? First of all, side FO of the pink triangle equals to side OD of the orange triangle. They are both the radii of the circle, therefore they are equal to each other. OF equals to OD. I will do it quickly because we already done it here in those two, the yellow triangle and the green triangle. It is actually the same process. side OF of the pink triangle equals to side OD of the orange triangle, above the area of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. Again, here CF equals to CD according to rule number 2. CF equals to CD. CF equals to CD according to rule number 2. And finally, we have side CO, that is a common side that belongs to both triangles. So we can write down that CO equals to itself. It's a common side that belongs to both triangles. Do it again. CO equals to itself. Okay, and finally, we actually proved that all the three sides of the pink triangle are correspondingly equal to all the three sides of the orange triangle. Therefore, we proved that those two right triangles can go into each other according to side rule. So I write it down. Prove that the orange triangle ODC can go into the pink triangle OFC according to side rule. And for the fact that those two right triangles can go into each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So this is actually angle CFO in the pink triangle, and it is equal to this angle OCD in the orange triangle. So those two angles are equal to each other. So actually, if we define one of those angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. Okay. If angle OCD equals to alpha, then the other angle CFO must be also equal to alpha. So alpha plus alpha, in total it is equal to 75 degrees. So 2 alpha equals to 75 degrees. Here we divide the equation by 2, and finally we get that angle alpha equals to 75 over 2 is 37.5 degrees. Okay. So actually, this is angle alpha that is equal to 37.5 degrees in its size. In the next step, I will copy the orange triangle ODC in the new page and we will analyze it. So this is triangle ODC, this is a copy from the original drawing. This is angle alpha that is equals to 37.5 degrees, and sine OD of the triangle equals to R, that is to say it is the radius of the circle. So in this triangle ODC, it is very easy to see that tangents 37.5 degrees equals to OD over DC. So tangents 37.5 degrees equals to OD over DC. So tangents 37.5 degrees equals to OD. OD is R, so we substitute OD by R over DC. So here we will multiply this equation by DC and we get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees, and finally we get that DC equals to R over tangents 37.5 degrees. So here this 97 DC is equals to R over tangents 37.5 degrees. So I write it down in the drawing. This 97 DC equals to R over tangents 37.5 degrees in its length. So it is very easy to see from the drawing that BC, side BC equals to BD plus DC. So I write it down, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC equals to 2 units according to what is given in the equation, so we substitute BC by 2, and it is equals to BD plus DC. So it is equals to BD, that is R over tangents 30 degrees, plus DC, and DC is R over tangents 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. So here we take R as a common factor out of those two expressions, and we get that two equals to R, so R was taken out as a common factor. What is left from this expression after we took from it R as a common factor? What is left is actually 1 over tangents 30 degrees plus R over tangents 37.5 degrees. So what is left from R over tangents 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangents 37.5 degrees. So in conclusion, we found out that 2 equals to R, and inside the brackets we have 1 over tangents 30 degrees plus 1 over tangents 37.5 degrees. So 2 equals to r, and 1 over tan 30 degrees, it is equals to 1.732 plus 1 over tan 37.5 degrees. 1 over tan 37.5 degrees equals to 1.3032. So if we found out the 2 equals to r times 1.732 plus 1.3032. So 2 equals to r, and 1.732 plus 1.3032 is equals to 3.0352. So in conclusion, found out that 2 equals to r times 30352. Here we will divide this equation by 30352, and finally we get that r, the radius of this circle, the radius that we are looking for, the radius r equals to 2 over 30352. That is actually 0.6589 units. So r, the radius of the circle, the radius that we are looking for, equals to 0.6589 units. Repeat again. In both methods, we found out that the radius r of this circle, it is equals to 0.6589 units. Okay, so we finished with the second method. In the next step, I will summarize the lecture. We start with the first method, of course. In this lecture, we found out the radius of this circle. So, in the drawing, we have a circle that is inscribed by this triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in its size. This is angle ACB that is equals to 75 degrees. And side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is inscribed by triangle ABC. In the first method, we did a construction, that is to say, from point C, we drew perpendicular on side AB. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. In this way, we are doing this construction, we created the right triangle CDB. Triangle CDB. So I call it the right triangle CDB in a new page, and we analyze this triangle CDB. So actually, this is triangle CDB that I copy from the original drawing. BC equals to 2 and again BC equals to 60 degrees according to what is given as the question. This again equals to 90 degrees according to our construction. So in this right triangle BDC, cosine 60 degrees equals to dB over BC. Okay, so dB, so cosine 60 degrees equals to dB over BC, and BC is 2. So cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2, so in total 1/2 equals to BC, 1/2 equals to dB over 2. Here we multiply this equation by 2 and finally found out that dB equals to 1 unit in its length. Here, this line segment dB equals to 1 unit in its length. Then we continue to focus on the right triangle DBC. On the right triangle DBC, sine of 60 degrees equals to DC over BC. Again, sine of 60 degrees equals to DC over BC. So sine of 60 degrees is equal to 3 over 2. That is equal to DC over BC. And BC is 2. So in total, square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally found out that DC equals to the square root of 3. Here, DC equals to the square root of 3. You can write down here that this 97 times 7 DC equals to the square root of 3 in its length. Then, in the sum right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have inside triangle DBC? We have this angle that is 90 degrees, this angle is 60 degrees, so in total 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle must be equal to 30 degrees in order to complete the sum of the angles in this triangle DBC to 180 degrees. The missing angle must be equal to 30 degrees in its size. So, the small angle DCB equals to 30 degrees. The big angle ACB equals to 75 degrees. Yeah, this is the big angle. The small angle equals to 30 degrees. So the big angle minus the small angle equals to the missing angle ACD. Again, the missing angle is the big angle minus the small angle. The big angle is 75 degrees minus 30 degrees. The small angle is 30 degrees. So 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle ACD equals to 45 degrees in its size. Then I copied the right triangle ACD in a new page and we analyze this right triangle ACD. This is the right triangle ACD that I covered from the original drawing. We just right now found out that angle ACD equals to 45 degrees in its size. This angle equals to 90 degrees. So the missing angle must be equal to 45 degrees in order to complete the sum of the angles in this right triangle ADC to 180 degrees. The missing angle must be equal to 45 degrees in its size. So angle DAC equals to 45 degrees. Those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle, they are equal sides. So those two sides, AD and DC, that are located in front of those two equal angles must be equal to each other. So side AD equals to side DC. But we have already found out that DC equals to the square root of units, so we can write down that DC equals to the square root of units. And from this equation, AD equals to DC equals to the square root of 3, we will derive that side AD also equals to square root of units in its length. So we can write here that this 97 AD equals to the square root of units in its length. Yeah, AD equals to the square root of units in its length. We continue to focus on the right triangle ADC. On the right triangle ADC, we implemented the Pythagoras theorem. According to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. So AC squared equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We took out of the equation and finally found out that AC equals to the square root of 6 units in its length. Here, side AC of this triangle ABC equals to the square root of 6 units in its length. Then I presented to you rule number 15, and we implemented rule number 15 in our drawing. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to R. The radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. So, in the drawing of this rule number 15, we have a circle that is inscribed by this triangle ABC, that could be any triangle. And according to this rule, rule number 15, the radius of this circle R, the radius R of this circle equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. And the semi-perimeter of any triangle is the perimeter over 2. So we can actually implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is described by triangle ABC. And therefore, according to rule number 15, the radius of this circle, we define the radius of this circle R, so the radius R must be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again, in our original drawing, the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter is this. So the area of any triangle is the base of the triangle times the height of the base over 2. The height must create 90 degrees with the base. In our triangle ABC, we choose the base as AB. AB is the base, and the height to the base is CD. Why? Because the height CD creates 90 degrees with the base AB. Again, the base is AB, the height is CD divided by 2. The base is AB, the height is CD divided by 2. This is the area of triangle ABC. And we have to divide the area by S. S is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter is the perimeter over 2. And the perimeter is the sum of the side lengths divided by 2. The sum of the side lengths is AB plus AC plus BC divided by 2. If you divide it by 2, you'll get the semi-perimeter S. Okay, so AB is equal to 3 plus 1 times CD. CD is equal to 3 divided by 2. It is the area of triangle ABC. And we have to divide the area by S. S is equals to AB that is equal to 3 plus 1 plus AC that is equal to 6 plus BC that is equal to 2 units according to what is given as the question. And when we divide the perimeter by 2, we get the semi-perimeter S. So the value of this expression that is actually the area of triangle ABC, it is equals to 2.366 square units. And the value of this expression in total, it is equals to 3.591. That's actually the semi-perimeter of the same triangle, triangle ABC. And 2.366 over 3.591, it is equals to 0.6589 units. And that is actually the radius of R of this circle that is described by triangle ABC. So the radius R of this circle equals to 0.6589 units. We finished with the first method. Then in the next step, I actually presented to you how to find out the radius of this circle according to the second method. In the second method, we define the center of this circle as O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together for a third time. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, therefore OD is R. OD equals to R. Here we have rule number 1. The radius OD is drawn to point D, that is the point of tendency of tangent ABC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. That is to say, this angle was 90 degrees and this angle was 90 degrees according to rule number 1. Likewise, we join points O and D together by side line. O is the radius of this circle that is equal to R. The radius OA is drawn to the point of tendency, that is to say it is drawn to point E. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, we join points O and F together by side line. Again, OF is the radius of this angle that is equal to R. The radius OF is drawn to point F. And therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we focus on the common external point C. From the common external point C, we have two tangents to this circle. Tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD according to rule number 2. Likewise, we focus on the common external point B. From the common external point B, we have two tangents to this circle. Tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. Here, BD equals to BE according to rule number 2. Then we join points O and C together by side line, and join points O and B together by side line. In the next step, we proved that the yellow triangle is congruent to the green triangle according to side rule. So why those two triangles congruent to each other? First of all, those two sides are both the radii of the circle, therefore they are equal to each other. In addition, side BF equals to side BE according to rule number 2. Here. Side BE equals to side BD according to rule number 2. Again, side BE equals to side BD according to rule number 2. BE equals to BD according to rule number 2. And finally, side BO is a common side that belongs to both triangles. So BO equals to itself is a common side that belongs to both triangles. So if we're going to find out that all the three angles of the yellow triangle BOD are corresponding equal to all the three angles of the green triangle BEO, therefore those two white triangles can go into each other according to side rule. And from the fact that those two white triangles can go into each other, we will derive that those two angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees according to what is given as the question. So here 2 theta equals to 60 degrees, divided this equation by 2, and finally found out that angle theta equals to 30 degrees in size. So this is angle theta that is equal to 30 degrees in size. Then I copied this yellow right triangle BOD in a new page and realize this right triangle BOD. This is the right triangle BOD that I copied from the original drawing. Side OD equals to R, this is the radius of the circle, and angle OBD is angle theta that is equal to 30 degrees in size. In this right triangle BOD, triangle is 30 degrees equals to OD over OB. So triangle is 30 degrees equals to OD, that is R, over DB. So triangle is 30 degrees in total equals to R over BD. We multiply this equation by BD and found out that BD times triangle 30 degrees equals to R. Then we divided this equation by BD, and we divided this equation by triangle 30 degrees, and finally found out that BD equals to R over triangle 30 degrees in its length. Here, this line segment BD equals to R over triangle 30 degrees in its length. Then we proved that the orange triangle is congruent to the pink triangle according to side rule. And again, side FO equals to side OD because they are both the radii of the circle, therefore they are equal to each other. Side FC equals to side DC according to rule number 2. And finally, side DO is a side DC is a side OC is the common side. This side OC is the common side that belongs to both triangles. So we can write down that OC equals to itself is a common side that belongs to both triangles. So we actually proved that the pink triangle OFC is congruent to the orange triangle OCD according to side rule. And from the fact that those two right triangles congruent to each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha is 75 degrees. So here 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that angle alpha equals to 37.5 degrees. Then I copied the orange triangle ODC in a new page and analyze this orange triangle ODC. This is the orange triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees. And side OD equals to R, that is the radius of the circle. In the right triangle ODC, triangle 37.5 degrees equals to OD over DC. Triangle 37.5 degrees, triangle 37.5 degrees equals to OD over DC. OD is R, therefore triangle 37.5 degrees equals to OD that is R over DC. Here we multiply this equation by DC and found out that DC times triangle 37.5 degrees equals to R. Here we divided this equation by triangle 37.5 degrees and finally found out that DC equals to R over triangle 37.5 degrees. So here this line segment DC equals to R over triangle 37.5 degrees. From the drawing it is very easy to see that BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC is 2, BD is R over triangle 30 degrees, and DC is R over triangle 37.5 degrees. So in total 2 equals to R over triangle 30 degrees plus R over triangle 37.5 degrees. Here we took out R as a second factor from those two expressions. And we have here 2 equals to R. So R is taken as a second factor. So inside the brackets we left only with 1 over triangle 30 degrees plus 1 over triangle 37.5 degrees. So 2 equals to R and 1 over triangle 30 degrees is 1.732 plus 1 over triangle 37.5 degrees is 1.3032. So 2 equals to R plus 1.732 plus 1.3032. And 1.732 plus 1.3032 equals to 3.0352. So in total we found out that 2 equals to R times 3.0352. We divided the equation by 3.0352 and finally found out that R, the radius that we are looking for, equals to 2 over 3.0352. That is actually 0.6589 units. So in both methods, we actually found out that the radius of this circle that is described by triangle ABC, the radius R, equals to 0.6589 units. Okay, thank you very much.